Hello and welcome to this session of Shadow the Scientist. My name is Jamika Marshall and I'm very pleased to serve as the coordinator for the Shadow the Scientist initiative. Tonight, you have the privilege of joining us as we shadow the team members of the Next Generation Virgo Cluster Survey Research Collaboration, which also includes the founder of Shadow the Scientist, GuhaThakurta, who is, along with his colleagues, going to be using it was scheduled to be using the Keck II 10-meter telescope to study rare galaxies called ultra-diffuse galaxies. With us, we have Raja and one of his other colleagues, Elisa Toloba, who I believe is leading the observations this evening. Hi, Raja. Hi, Elisa. Welcome.
Hello, everyone. Elisa, if you wanted to introduce yourself, and then I'll do the same afterwards.
Okay. So I'm Elisa Toloba. I am a professor of physics and astrophysics at the University of the Pacific in Northern California, in Stockton. I work on galaxy formation and evolution. I have been working since my PhD in a region of the sky called the Virgo cluster, where thousands of galaxies live together in the direction of the Virgo constellation. And we are scheduled today to observe a very special class of galaxy in this cluster. But Raja, if you want to introduce yourself, and then we can talk about the project a little bit.
Okay. Let me just see. Okay, so I'm Raja GuhaThakurta. I'm a professor of astronomy and astrophysics at the University of California, Santa Cruz. And this is Santa Cruz is a home of where Shadow the Scientist started as a program. Jamika and I are UCSC colleagues. Jamika is based in Hawaii. I'm based in Northern California in Los Altos. Elisa and I worked together for years. She was a postdoc at UCSC when we started working together. A postdoc position is what you do after you finish your PhD, and Elisa's first postdoc position was at UCSC, and before she started her faculty position at the University of the Pacific. So Elisa and I have been working together for how long? 10 years, close to that. On galaxies in the Virgo cluster. My own research on galaxies in the Virgo cluster goes back a long way. One of my very first research projects, the first research project I ever published as a lead author was on the Virgo cluster, and that was back in 1988. So long time ago, over 3 decades ago, when I was a graduate student studying galaxies in Virgo. So tonight we're going to study ultra-diffuse galaxies if the conditions permit. What has happened, if you've been, I don't know if you've been following what's been going on in Hawaii, but the Kilauea volcano on the Big Island has been very active. It's been spewing, volcanic ash into the atmosphere, and the particle count of essentially ash particles is high enough that we're watching that drop gradually before we can observe, before it's safe to open the telescope. So here we are. It's a half night on the telescope. We are supposed to work until a little after midnight Hawaii time. And right now it's about 8:15, a little before 8:15 Hawaii time. Right, if I have that correct, yeah, it's about 8:15. 8:14. We will share our screen. I can show you some spectra of things that we've collected in the past using Keck. I have that set up to go when I heard that we may not be so lucky as to start our observations on time. Normally by this time we would be doing some calibration exposures. The sky is not completely dark yet after sunset in Hawaii, Right, Elisa, when is 18-degree twilight? Is that close to 9? Hawaii time? No, earlier than that. Earlier than that. I have to look up when.
Close to 8:30.
Okay, so it's coming up in 15 minutes. So just 18-degree twilight is when the sun is 18 degrees below the horizon, and the sky, when it's right at sunset, that means the sun is at the horizon, 0-degree twilight. The sky is still quite bright, as you know, from sunlight. When it's 12 degrees below the horizon, significantly darker. And beyond about 18 degrees, the sky doesn't darken more than, appreciably doesn't, what am I trying to say? When the sky is 18 degrees versus 20 degrees, 25 degrees, there isn't much of a change. Jamika's sharing the Mauna Kea camera, and I can share my screen and bring that up. Jamika, did you want to say anything about the Mauna Kea where the camera is?
No, go ahead.
Okay. I'm displaying one of those cameras right now. This is looking at the Canada France Hawaii telescope. Oh, this is from the Canada France Hawaii telescope, I guess, from the catwalk of that telescope. And this is a time lapse. But if I go back, the basic problem now is volcanic ash in the air. But these are time lapses, recent time lapses. This one is from the Subaru telescope, looking at the 2 Keck telescopes. Very recent time lapse leading up to the present time. So you can start to see stars in the sky now, as you can tell. I'm going to go back home. Oh, no marking on the screen, please. Thank you. As usual, we have images of the kinds of galaxies we're going to be looking at if and when the conditions permit. But we also, like I say, also have spectra taken with the Keck telescope that happy to share. I suggest I stop my screen share for a moment while we go around the room. We still have a fairly small group here. Jamika's introduced herself, Elisa has, I have. Daniel, would you like to say a few words about how you got connected to Shadow the Scientist? Again, feel free to share whatever you'd like to. Oh, thank you. Daniel, would you like to share how you found out about Shadow the Scientist? And
I'm not Dan. I'm a friend of his, and
oh,
he
okay.
forwarded the link to me.
No problem, of course. I think someone else has joined with the same name, Daniel Reed. So I wonder if that's Dan.
Probably, yeah.
Okay.
Yeah, that's me.
Hey, Daniel.
Hi.
How did you find out about Shadow? I'm just curious.
It was emailed.
Okay. Where are you connecting from, if you don't mind my asking? Okay. Is that in Hawaii?
Yes, sir.
Okay. Okay. Fantastic. Okay. And I know we have a few others who are connected. Rob, you're a regular from Southern California. Please feel free to introduce yourself.
Sure. I'm Rob Johnson. I'm zooming from Los Angeles. I'm a mathematician, amateur astrophotographer, and a software engineer. I found out about Shadow the Scientist through Griffith Observatory. They're all space considered. And about it.
Thank you, John. Thank you, Rob. Jamaica, you had your hand up for a second. Did you? I wanted to make sure I didn't. If you wanted to say something.
No, it was a wave. I was just waving to Rob.
Oh, thanks. Okay. Daniel and Daniel's friend, welcome. Welcome to Shadow the Scientist. Is this the first time on Shadow the Scientist for both of you?
It's been a while. Not the first time, but it's been a while.
Okay.
Diogo, you're awake.
Yeah, I'm in Boston. It must be 2:20 a.m.
Yeah,
Right.
it's very late for you. Wow. So one of you is 3 hours ahead of California. It's 11:20 for me. One of you is 3 hours behind. So it is late. Let's see. Julie or Cassie, would you like to introduce yourself? I would love for you to say a little bit about what say a little bit about your roles at Keck. Would love for that.
Sure. Julie, you want to go first since you're the OA tonight?
Hi there. Yeah, sorry, I'm just getting in. Trying to get warmer. It's a little bit of a chilly night here in Waimea. My name is Julie, and I'm the observing assistant for Keck Observatory. I'm working on Keck II tonight with Raja and Elisa. So, what did you wanted me to just, sorry, I didn't quite hear you, just introduce myself?
Oh, Julie, if you could, just say a little bit about your role and what an OA does at an observatory, that would be amazing. Part of these sessions are to demystify the people behind the process, of course. I'd love for you to, if you feel comfortable.
Awesome. Yeah, so an OA stands for what we call observing assistant. Some other telescopes have similar positions, oftentimes calling them telescope operators. So basically what happens is for a large telescope like we have here, a person like me is trained to be able to run the telescope and point it where the observers want to be looking to get their data. In some cases, they might run the instruments themselves, like at Gemini, where it's somewhat Q, or it's a Q thing. But here, I basically just control the telescope while the observers control the instrument and take their data. And I'm kind of the first line of defense against any problems. So if, there's issues that come up, then I either figure out how to fix it or figure out who to call to fix it, make weather decisions and things like that. So that's pretty much my role here. There's 9 of us, I think, altogether, because we have to cover both telescopes every single night of the year. We're even open on Christmas.
So, Julie, what does a shift look like for you? How many nights are you on and how many nights are you off?
So the standard typical shift would be 5 nights. The first night being an overlap night, where basically I'm acclimatizing either to the summit and both to the to getting used to being on a night schedule. I have young kids at home, so I go from like getting up at 6 a.m. to sleeping all day and getting up for the night and working all night long. And so it'll be 1 overlap night and then 4 nights where I run the telescope all night long, and that can be like 12 to 14 hours depending on the time of the year, how long the night is. And then I get at least 7 days off. Sometimes it's more, especially if people aren't really getting sick and everybody's healthy and things like that, and people aren't taking vacations. Sometimes it can be a little bit less, but rarely does it go less if we're, if we've lost a lot of people are sick or something like that.
I see. How long have you been at Keck, Julie, if you don't mind my asking?
I have been here since 2002, so nearly 22 years. I came
Wow.
here pretty much, I mean, I did a little bit of stuff after college otherwise, but I came here pretty much after after graduating from undergraduate college.
I see. You've been at Keck as long as Demos has been at Keck. Demos was commissioned in 2002.
Yeah, I was there around then, and I was there for the early days of the laser, the first Keck II laser, that was the dye laser. Yeah, I've been here a little while. I'm
I think
I'm the oldest OA currently
Wow,
here.
okay.
Everybody that was older than me has retired by now.
I think my first night on Keck was 7 years before that in 95 when there was no remote observations. You're in Waimea
Mhm.
tonight, but back then,
Yes.
Waimea, you couldn't observe from there, had to go up to the summit. I remember back in the mid and late 90s.
Yeah.
Oh, thank you. That's very very helpful. Thank you.
You're welcome.
And Cassie, would you like to take a moment to introduce yourself? I hope I've spelled your name correctly in the Zoom.
Yes, you did.
Okay.
Thank you. Cassie, I'm the night attendant that night. So I'm up on the summit. Basically, I'm up here to for the remainder of the night be on standby to resolve any on-site technical issues that we may encounter. And I've been at Keck about 1 year now. So this is relatively new for me.
Sure.
Yeah, that's about it. I work a similar shift to the OAs like Julie.
Okay,
4 days on, 5 days off.
got you. Well, thank you so much for helping us tonight. You too, Julie. Thanks. I know that none of this would be possible without the amazingly dedicated Keck staff. You guys always get an A+ in my observing report. If that's the only
you
A+ in my report, it's always there. That's
Thank you
something
so
that
much,
never changes.
Raja.
Oh, of course,
Also,
of course.
I just want to say that, I wouldn't even have this job, which I love very much, if it wasn't for observers like you. So thank
Oh, thank you, thank you.
you.
Oh, thank you both for introducing Cassie and Julie. And let me see if the others would like to introduce themselves. Alankrita, I'll go to you next, and then I'll go to Nihal and then Daisy. Alankrita, if you want, please unmute and introduce yourself. We're a small group.
Hi, I'm Alankrita.
Hi.
So I'm starting in high school this year, so a bit nervous. Yeah. So I heard about this from my counselor and I was pretty excited, So chemistry and physics are actually some of my favorite subjects. So I was like, let's try this out. So yeah, I'm very excited to be here.
Where are you connected? What time zone are you in?
So I'm in Hyderabad, India. So it's 11:57 a.m. right now.
I see. On a
Morning.
Friday.
Yeah.
Midday.
It's going to be midday, yeah.
Yeah, close to midday, right? You're must be 11:57.
Yeah, 11:57.
Yeah, fantastic. I'm so glad you're connected from there. Alankrita, your counselor, do you know how they found out about Shadow the Scientist? Was it through a conference there?
I think she has like a meeting with other teachers there, so she mailed us about it. So I'm not really sure how she found out about it.
That's fantastic. Please thank her on my behalf and Jamaica's behalf. Our team, one of Jamaica's colleagues, Jamaica and my colleagues and I, we were in Hyderabad at the, what's it called, High Tech City, for a conference at the Novotel Hotel last August, and then the August before that as well. And there we certainly advertised Shadow the Scientist. I'm wondering if your teacher found out that way. Well, welcome.
Yeah.
Good luck
Thank you.
with high school. And I just want to mention this specific to you, perhaps, but I don't know how old Nihal and Daisy are. But Shadow the Scientist is one of 3 big programs that we offer. And in Shadow the Scientist, you get to meet scientists like us. You get to meet other science enthusiasts like others on the call. You get to see a little bit about the kind of research that scientists do, in this case, astronomers. But Shadow the Scientist Jamaica has set up sessions that are in biology, stem cell biology, forest ecology, 2 flavors of biology, but also in oceanography and study of the Earth's climate history. In other words, today you're shadowing astronomers, but you could shadow other scientists. There are multiple sessions. Yeah, because just put the web page there. We run a bunch of programs. Shadow the Scientist is one of them. It's the entry program, if you like. If a young person hasn't engaged in science research before, this is a great way to enter the field of science. I'm going to use an analogy for someone who's looking to swim in the ocean. The first thing you want to do is dip your toes in the water of a swimming pool, see if the water temperature feels right, and if the people in the water are welcoming, and if they're having fun doing what they're doing. Shadow the Scientist is that to all kinds of research. It's dipping your toes in the water of science, getting to see those who are already in the water, so to speak, to use this analogy, and to see if they are welcoming and if they're having fun. Then we have a program where you can learn the swim strokes. Again, I'm using an analogy. So we teach Python programming. We have a session next week. We offer it 3 times a year, once in February, once in June, and once in November. It'll be late at night for you when we offer it. It'll be 10 to noon our time, which is 10:30 p.m. to 12:30 a.m. India time. But we teach Python coding, and for students or for anyone at any level, it's free, it's online, just like Shadow the Scientist. And then a third program we run, that's like swimming in the ocean after you've learned your swim strokes. And that's a program called the Science Internship Program, and that starts on Monday for us. And it's for high school age students from all over the world, including students from Hyderabad and students from other parts of India have applied to our program, and some are going to take part of the program this summer. Anyway, that's a long explanation of what we do. Nihal, would you like to take a moment to introduce yourself? Feel free to if you'd like to. Yeah, go ahead.
Hi, my name is Nihal, and I'm pretty much the same as Alankrita. I'm in 10th grade, and I live in Hyderabad too. I heard about this from my school counselor as well. And
fantastic.
Yeah, these days I've been really interested in astrophysics and computer science, so I wanted to try this.
Fantastic. Welcome, Nihal.
Thank you.
Daisy, if you would like to introduce yourself, please take a moment to do so. But again, don't feel pressure if you'd like to, please say who you are. Oh, there you go. Okay, thank you. Thank you so much. Oh, well, you found out about it through SLI at Foothill. Yeah, we were recently there at Foothill presenting during your during the possible self STEAM event. That was a few weeks ago. I'm actually located very close to Foothill College. My home is very close to Foothill College. But thank you for connecting, Daisy. All right, let's get a quick report from Julie about the conditions on the summit. Any good news for us, Julie?
Well, the humidity just came out of the red. We use red for can't open, yellow for be careful, we might be heading towards red, and green is all good. So yeah, our humidity has been high tonight, and we also have quite a few dust particles in the air, most likely caused by the recent volcanic eruption down in Kilauea. So we've been monitoring those 2 things. We want to make sure that dust doesn't get stuck to the mirror by moisture. But yeah, the humidity is trending, is just moved to a good trend. So maybe in half an hour we'll get to try the test to see if we can open and get our dust counts down.
Thank you. If it's okay then, while we're waiting for that, I'll share some spectra that we've collected from Keck. Elisa, I have some spectra from our Andromeda work. I have 2D spectra. I have Z-spec running on one of my virtual desktops, so I can share that if you like. Unless, is there anything in particular, Elisa, you wanted to talk about before that or after? What do you think?
No, you can start the show in what
Okay, I'll do
that
that.
can look like.
Yeah, I mean, the other options we can, while we're waiting for the telescope to open, I think in the past, we've shared Sang-Soon's paper and your paper, we screen shared, talked about the kind of science we've already done using measurements with Keck, for example, and Keck and other telescopes. And then I, of course, also have that browser that shows pictures from the NGVS of galaxies. So these are different possibilities for us.
Yeah.
I'm also, if anyone is interested, young and old, anyone is interested, I'm happy to talk about our other outreach programs or more about Shadow itself. Please spread the word. We are, Jamaica in particular has been hugely instrumental in building the Shadow the Scientist program to where it is today. She's also helping build the Python and Research program. Jamaica and I have colleagues who have helped build the Science Internship program, and Foothill students are actually involved in the Science Internship program as well. It's mostly for high school students, but we have slots for Foothill students, and many have taken part over the years, and happy to tell you more about them, and if you'd like to spread the word about them to others who might benefit from these programs, please do so. This is where, UCSC is a nonprofit state university, and our programs under it are also nonprofit programs that are designed to demystify science. And we work under the umbrella of something called CREST, Creating Equity in STEAM. And this is really the mission of the program. Our name is the mission. All right. I will share my screen next. And at any point, please feel free to, we're a small group, feel free to ask questions of what you're seeing here. I wanted to introduce a concept that I was explaining to one of my students earlier today. One of my research students earlier today is working with what we call 2D and 1D spectra. So a spectrum is a glorified rainbow. That's what it is. I'm going to show you a spectrum here. Something like this is called a one-dimensional spectrum because you look at intensity on the y-axis as a function of wavelength. This is wavelength on the x-axis. Wavelength is a measure of the color of light. So red light would be sort of here somewhere. This in the left half of the spectrum correspond to red light. The right half of the spectrum correspond to infrared light that the eye can't actually see. So we take the light of stars in Andromeda. What you're seeing here is a spectrum of an actual star in the Andromeda galaxy. We split it up into its components. We don't, the spectrograph does. Tonight, we're planning to use an instrument that also splits up the light into its constituent wavelengths. Tonight's instrument is fancier because it creates 3D data cubes. It creates a spectrum at each point in the sky, whereas DEIMOS creates spectra at a limited set of stars. It is what is called a slit spectrograph, but it's a multi-object slit spectrograph. DEIMOS is, whereas something like KCWI and KCRM, which is what we're planning to use tonight, that's called an IFU, integral field unit. You can think of it as taking a spectrum of each pixel within a rectangle on the sky. So what you saw in the black background with the white lines, this is a 1D spectrum. There are several features here. You notice this little, the spectrum, if you can see my cursor, it gradually rises, but then goes through this kind of dip, does the same thing again over here. This is actually caused by the molecule titanium oxide in the atmospheres of relatively cool stars. These stars are cooler than the sun. Their surface temperatures are between 3,500 and 4,000 Kelvin. The sun's surface temperatures closer to 6,000 Kelvin, 5,800 Kelvin. So these cooler stars, the surfaces are cool enough that molecules like titanium oxide, vanadium oxide can exist. In the surface of the sun, the temperature is high enough that these molecules get dissociated by particle collisions. So even the presence of molecules in a star's spectrum tells us immediately about its temperature. It also tells us about its chemical composition, of course. So let me just see what I was doing here. I have these very cryptic notes here that you're looking at. But you're also, in this particular window that I just brought to the front, this is something called a two-dimensional spectrum, where you can think of a spectrum as repeated images of a slit. And if you look closely, you'll see these tilted lines. These are repeated images of the slit that was used to collect the spectrum. This particular spectrum is that of a star in Andromeda, like I said. You'll see this very sort of black and white peppery thing in the upper band. This is caused by a phenomenon called vignetting, where the detector, the silicon detector, this part of the detector is not receiving any spectral light, and the process of flat fielding then amplifies the noise. So what you're seeing is just pure noise in the upper band, the left part of the upper band. If I march along this, if I march to the right along this, you'll see that that noise is just limited to the upper left. Let's see, there we go. There's a spectrum. It's this very long band. You're seeing a zoomed out version in this screen, and a sort of very zoomed in version on this screen over here, and then sort of a moderate zoom in the main rectangular window here. So I'm marching to the left, and you see it's like line 2 sentences in a book. The top row is read from left to right, and then when you get to the right end of the top row, then you go and read from the left of the bottom row again to the right. And the green window is bouncing around as I pan through this window, as I pan through the main window. This green window here, you'll see it bounce to the right as I move. What is remarkable is from a spectrum like this, which looks quite noisy, if you look at this spectrum, it looks quite noisy, there's enough information that we can determine the velocity of the star. And it really comes from titanium oxide. It's this very sharp dip here between the model and the data. You see the sharp dip, and that is enough to say, yes, we can, we know the velocity of this object. You can see other features here, like these two dips here, marked by the dotted lines, are the expected dips produced by sodium in the atmosphere of the star. So this has a reliable velocity. You can see it's given as equality of 4. Its velocity is, let me just save something here, and let me auto re-extract. Let me see what that gives me. Yeah, spectrum didn't change much, but let me pause here and see if there are any questions about what you've seen so far. And no question is too basic, really. Anyone feel free to ask a question about the spectrum you're seeing, or even these cryptic notes that I'm writing down here. No questions at all? Is my explanation of a 2D spectrum something that's clear? So the 2 dimensions are wavelength running from left to right and position along the slit running from, bottom to top or top to bottom. Here's a beautiful spectrum. This time you see these very strong dips. These are produced by singly ionized calcium in the atmosphere of the star. And if you look closely, you'll see two spectra, not one. The white spectrum is the spectrum of the star in Andromeda. The blue is what is called a template. It's a spectrum of a star whose velocity we know. And so if we Doppler shift the template by a known amount until it matches the spectrum of the star in Andromeda, this is done by software, we don't do it by hand, then we can read out the velocity. And this particular star has a velocity of minus 494.5. It's in kilometers per second. It's moving towards us. Minus means it's moving towards us at nearly 500 kilometers per second. So I'm going to re-extract its spectrum. And again, you get this beautiful, this is actually a special kind of star that our group recently discovered. It's something called a weak CN star. It has this sort of undulations right around. It's got a very subtle bump right at 8,000 with two dips on either side of it. Let me see if I can smooth the spectrum to show this to you a little better. You see there's a very subtle bump at 8,000, a subtle dip to the left of 8,000, subtle dip to the right of 8,000. This is something called a weak CN star. So I'm going to make a note of that. This big dip of this big glitch here is due to this bad column running through the spectrum. So I'm going to make a note of that. This particular kind of star, this particular kind of spectral feature is something our group discovered recently, and we are actually in the process of writing a paper. It's a paper that I'm supposed to submit this weekend. It's a paper that I'm leading. It won't contain this star in it, but we've found other stars like this before, and that's what this paper is about. Weak CN stars, they're called. CN is cyanogen. Again, we're talking about the chemistry of stars. Carbon and nitrogen combined into a molecule, and their presence in these kinds of stars was sort of unexpected, and that's what this paper is about, is reporting this discovery of cyanogen molecules in this particular class of stars. And you might wonder, so what? So what they found cyanogen? Cyanogen has been found in other stars where we understand why it's present in the atmospheres of the stars, that we understand the underlying physical processes of how the stars' interiors evolve and how carbon gets dredged to the surface. But for these stars, there's no clear understanding of why the carbon makes it to the surface of the star to bond with nitrogen to produce CN. The presence of nitrogen is understood, but the presence of carbon is not. So this research helps us understand how stars work, how, in this case, how massive stars work. These stars that we are studying, that we found this phenomenon in, the spectral feature in, tend to be 5 to 10 times the mass of the sun, so significantly more massive than our sun. And they're in a stage of evolution where they're called red supergiants, and they're actively converting helium into heavier elements through nuclear fusion in their core. The sun is converting hydrogen to helium, but these stars are called core helium burning stars. That means that in their core, helium is being not burnt, but burning is a sort of a sloppy term for nuclear fusion in this case. Helium is being converted through fusion into heavier elements in these stars. Okay, now I've thrown a lot of information at you. Let me stop sharing my screen for a moment and see if people would like to ask any questions. Yeah, heavier elements, indeed. After helium comes lithium, then beryllium, boron, etc. Helium is indeed helium is the second element of the periodic table. The third is lithium, beryllium, boron, carbon, nitrogen, etc. This star will die soon after that. In fact, 5 to 10 solar mass stars typically die through supernova explosions. But soon is relative. Soon is still millions of years, rather than soon in the human context. For humans, soon means minutes, seconds, but for a star, soon could still mean a very long time compared to human lifetimes, because these stars live for millions of years, in some cases close to 1 billion years. But it's a good way to put it is the star is, in a fractional sense, it's close to the end of its life, meaning it's lived out 95, 99% of its life. So in that sense, it's close to its end, but not in the sense of it's not seconds away from blowing up. It's millions of years from blowing up. Or 100,000 years from blowing up, that level. Thank you for asking, Alankita. That's great. One of you said you're really fond of chemistry. Who was that? Was that Nehal? No, maybe it was Alankrita. You said you're fond of chemistry.
Yeah, it was me.
One of the cool things about astrophysics is you get to study physics, chemistry, math, statistics, all of those things. It's just applied to things in space rather than things on the Earth. But we often have to do experiments on Earth to better understand the things in space. And Jamaica, Elisa, Cassie, Julie, at any point, if you wanted to chime in with any aspect of anything, please feel free. And that could be a question, that could be a comment, could be any aspect of your work. Please feel free. I was just talking about, I was showing you these spectra. By eye, now I know how to recognize one of these weak CN stars, but let me share a draft of the paper that's about to be, that we're getting ready to submit. I think I have a copy of that on this page somewhere. Do I? Don't know if I do actually. See if I can find it. Just give me a moment, sorry. No, I don't have it handy here. I have it on my other computer, but not on this one, sorry. Otherwise, I would have been able to show you. I might be able to bring it up, let me. We use some software called Overleaf to write papers. It's something that a lot of astronomers use to write papers. Oh no, it's making me go through all this.
I just noticed the question of how do you create a spectrum. I thought maybe I could try to answer that, Raj.
Please do, of course.
What you're doing. Creating the spectrum is part of what happens here at the observatory. The observers will come with a list of targets, stars that they're interested in, maybe galaxies, whatever they're interested in. We also look at moons of Jupiter sometimes, and we'll point the telescope there, and most of the instruments on the telescope will create a spectrum. If you've ever used a prism or seen anything about like the slit experiments, where if you direct a beam of like white light towards a very, very thin slit, or through a prism, you'll see it separate out into the rainbow, right? I mean, you can even see this in the skies, especially here in Hawaii, when we have a relatively sunny day, but it's raining and there's some clouds around, then we'll get a rainbow, which is basically the white light being spread out into a spectrum. So that's what our instruments do, is they'll have what Raja was talking about. It'll have a slit, a very, very, very thin slit, so that when the light hits it, it gets spread out into the large range. And when astronomers talk about light, it's a lot more than just the visible light. The visible light is a very small part of the entire spectrum. There's the infrared above the red side, ultraviolet, and on, radio waves are radio telescopes. So we are, as a Keck Observatory, is a mostly visible and infrared telescope. So most of our spectrum are going to be in that general range. And yeah, and then we have CCDs, which are basically like the cameras, even in your phones, that you might have that take pictures. We open it up and it collects the electrons caused that are excited by the light. I'm not explaining this well, sorry, Raja.
You're doing a
But
great
yeah,
job,
so
Julie. You're doing a great job.
We have CCD cameras that will pick up this light, and so we, you use the prism or the slits to spread the light out, and then it falls on different parts of the CCD, and so that's how we actually capture the spectrum, and then that gets written to a file, like the file that Raja was showing us earlier. So it's not the greatest explanation, but
no, it's a great explanation, Julie. I was going to say that I was going to just add a couple of quick things. There are probably folks in this, and there are probably folks who know Pink Floyd better than others, but their Dark Side of the Moon album is a great illustration of a spectrum. You have a white light, a ray of white light coming in, sunlight coming in, goes through a prism. The prism is faced with its pointy side up, base at the bottom, and violet light bends the most, red light bends the least. So you start with, if you didn't have the prism, you'd create a white spot on a screen, but instead you get a line with violet at the bottom, red at the top, because the violet light has been bent more than the red light by the glass air interface. The other thing I was going to add is this business of CCDs and light hitting a piece of silicon, releasing an electron, is related to something that Albert Einstein got the Nobel Prize for, which is the photoelectric effect. And that was a paper that he wrote in 1905. So we're talking about 119 years ago. That was a miraculous year for Einstein because he wrote 3 papers that were each Nobel Prize worthy. One was the photoelectric effect paper, one was about Brownian motion, and one was about special relativity. He got the Nobel Prize for one of those 3, photoelectric effect. But that's the basis of how CCDs work. Light comes in. Einstein said, let's think of light as bundles of energy, packets of energy, photons. Before that point, light had been thought of as waves, thanks to James Clerk Maxwell, after whom there's a telescope named on Mauna Kea, but the JCMT telescope. But Maxwell's description of light as a wave and Einstein's description of light as a bunch of particles, bundles of energy, are actually not incompatible with each other. Today, we know to think about light in what is called wave-particle duality. Light exhibits particle nature and wave nature. And that was one of the sort of brilliant discoveries that Einstein made that led to the Nobel Prize. And now we know that even particles behave like particles and waves. And so wave-particle duality applies to everything, to light and matter. I have my paper ready to share. But before I do that, did anyone else want to chime in with anything? Please feel free. Tarsi, you look like you're about to say something. Are you getting ready to say something or no?
I'm sorry, I was just adjusting my position.
No, that's fine. That's fine. Sorry to put you on the spot.
I did study chemistry though, so this is all in line with my interests, and KCWI as an instrument, it's broadly of interest in the research that can be done with it. So, yeah.
Yeah, our team, Elisa and I, are relatively new users of KCWI. I've been using DEMOS for as long as it's been around, for the 22 years it's been around. But KCWI is a newer instrument, and I haven't used it as much as some other people in the Keck community. Many years ago, I used a different IFU. It's actually a Fabry-Perot instrument that was built at Rutgers. And KCWI has lots of similarities to that. Same principle of taking a spectrum of each patch, of each pixel in a patch of sky. I was going to share my paper briefly. See if I can do that here. Yeah, this is a paper we're getting ready to write again. CN, as in cyanogen, spectral absorption feature. It's a weak feature, it's not a strong feature. And we think the stars that exhibit this are red supergiant stars. This particular paper is about stars in two galaxies, Andromeda and Triangulum, whose nicknames or code names are M31, Messier 31, and Messier 33. You can see there's a bunch of us working together on this. Doug is a PhD student at Santa Cruz, who's been a key player in this work. Antara is actually an undergraduate at Harvard, but she was a high school student when she started working on this project with us. And there are various stages in this, various people in this paper at different stages of their academic careers. Most of the others in this paper, most if not all of the others in this paper are either undergraduates or graduate students or faculty. Anyway, so you see this very sharp W feature. That's what you see in what are called carbon stars. And weak CN stars have a very subtle version of this W. You can see a very subtle version. It's still W-shaped, but the overall baseline, the overall intensity of that W, the depth of the two dips in the W are much less pronounced. That's why weak CN in this class of stars than the one on the left. These are 6 different stars, all in the Andromeda galaxy. These stars, carbon stars, are relatively well understood. Weak CN stars is a discovery by our group, and no one's, at least no one that we know of, has talked about this in the literature before us. So we are presenting this anyway. Papers are long, they have all kinds of plots in them, equations occasionally, more plots, and lots of text, more plots, different kinds of plots. These are what are called color magnitude diagrams. They're like Hertzsprung-Russell diagrams. These are plots with models against them, and so on. And then finally, we write our conclusions. This is conclusions, what we're going to do in the future, what we're planning to do in the future. We acknowledge a bunch of people here, a bunch of grants, and then we go on to citing or listing the references that were cited in the paper. These include papers that our own group has written in the past, papers written by other people on topics that are related to weak CN or carbon stars. Anyway, I will go back to looking at these spectra. But any questions about the paper before I show you more of the spectra? I'm not seeing any questions in the chat or in the audio, but feel free to ask at any time. I'm going to share my screen again and show more spectra. Let me get a report from, let's see, let me take this moment to get a report from Julie. Still in the yellow? the humidity?
So yeah, we've been out of the red for 25 minutes now. So I would say that we gonna try our opening experiment in 5 minutes. So however, the trend is starting to turn around. So hopefully it stays.
Where are the particle counts, Julie? What sort of is there any measure of that?
Yeah, so we have a couple different dust sensors, most of them inside, and those are a little on the high side, whereas our outside dust sensor is showing a lot of a big drop. Our traditional, we didn't have an outside external dust sensor a year ago when Mauna Loa started erupting, so we don't really have a good feel for what that would look like. So that's kind of why we're trying the experiment tonight.
Got it. Got it.
Or why we'll be able to try the experiment tonight to see if that decrease in the outside one is going to correspond to a decrease in the inside one.
In the inner one.
And exchange air through. Yeah. Mm-hmm.
Gotcha. We are very happy to be part of this experiment. So I hope you learned something from it.
Yes. Hopefully we can get open and get you guys
Okay.
data.
So fingers crossed that you think in a 5-ish minutes, unless the trend turns around.
Yeah.
Okay. Please interrupt me. I'm going to take the question from Alankrita in the meantime. Please go ahead, Alankrita.
Yeah, so for the paper that you're writing about the weak CN and carbon stars, so what kind of instruments did you use to find out what you're writing about, and how long, like, approximately did it take for you to get the findings for this paper?
It's a great question, Alankrita. Let me answer the two parts to your question. We used two main telescopes/instruments for this paper. One of them is the Keck telescope that we're on tonight. Keck has two telescopes, Keck I and Keck II. Tonight we're on Keck II, and it's the Keck II telescope that was used to collect the spectra. The spectrum is the main part of this paper. So the telescope that was used is the telescope that we are planning to use tonight. The telescope focuses light, of course. Once the light gets focused, that focused light goes into what's called an instrument, the thing that splits it up, say, into the colors of the rainbow, like Julie described. That instrument is different from the one we're using tonight, but that instrument spectra are what I was sharing with you and what I'm about to share with you again. These spectra over here come from what is called the DEIMOS spectrograph. I'm going to put the name in the chat. DEIMOS is the name of the spectrograph. It stands for Deep Extragalactic. I'll type out the whole thing in the chat. That's the first part of your question, was what instrument was used. Give me a second. I'll type this out. Deep Extragalactic Imaging Multi-Object Spectrograph. Deimos is also one of the names of one of the moons of Mars. Mars has two moons, Phobos and Deimos. Deimos means awe, as in AWE. Phobos means fear. So, so this is the Keck II telescope and Deimos were used to collect the spectra. We also use in this paper, we use brightness measurements of the stars that were made with the Hubble Space Telescope. Now, it's a great question as to how long this took. This is an unusually long project. The first time we noticed some anomalies in these spectra was over 10 years ago, a little over 10 years ago. I remember I was working with some students and we noticed this, and I asked the students to look more into this, and we couldn't quite make sense of it back then. We've made more sense of it now. We don't still fully understand the physics behind what produces this enhanced carbon and CN in the surface. So in this case, a little over 10 years ago, when we first noticed there was something different about these spectra. Does that answer both your questions, Alankrita?
Yeah. It's fascinating to know how long like a project like this would take and the technology that goes on behind it.
Yeah, and things don't always take this long, right? So I'll give you a counter example. one of my students, a PhD student of mine, working with a few others, published a paper that came out 2 months ago, came out in April, right? While we were writing this paper, we came up with a particular formula, like just what they call a heuristic formula that's based on some basic principles. We said, here's a formula that we think makes sense. We didn't have a full proof of it, like mathematical proof, like in geometry you have theorems where you have proofs. So this one, we didn't have full proof of it, but from a common sense standpoint, applying physics principles, it sort of made sense, right? So we put this formula into the paper. It went through a refereeing process. The referee didn't object to it, didn't comment on it at all. And so this formula is published. So we came up with this formula a little over a year ago, right? I came up with this formula a little over a year ago. Last summer, I was working with a bunch of high school students in this science internship program. Remember I described we run these 3 programs. In the 3rd program, the one that's like swimming in the ocean, high school students help us with our research in that program. So I said, look, we have this formula. There's a way to test it. Here's some data, let's test it. And they started testing it, and they found that the formula looked like it was valid. So we're getting ready to write that up into a paper. So that one, it's the idea of the formula maybe was about 1.5 years ago. The idea to test the formula was less than a year ago. And we're already thinking of writing it up into a paper, and we'll probably start writing the paper this summer. So it's a shorter lead time, almost 10 times shorter, instead of 10 years, 1 year. Sometimes people publish things on a much shorter time scale. If there's something exciting, new discovery, or something changes, like an exploding of a star, things like that, those get published on much shorter time scales even. There's a wide range.
Okay, good to know.
I don't want to, in any way, give the impression that it always takes 10 years to do something that's publication worthy. No, not at all true. Sometimes people write papers on things that they've been working for even longer than that, but more often than not, projects are shorter than that, quite a bit shorter in some cases. Other questions from the group? Or from you, Alankrita, if you have other questions.
Oh yeah, I did have another question actually. So the technology that you use, like Deimos, like I don't know how to pronounce that.
Demos,
DEI.
yeah, Demos.
So like when did this come into picture? Like when was it invented? And exactly like do you know how it works? Like in a kind of rough way?
Absolutely, absolutely. So Demos as an instrument, one of my colleagues led the effort to design and build it. It was first used in 2002, so 22 years ago, first used on the telescope in 2002. And it's been in regular operation since then. But it took maybe 5 to 8 years before that to go from design to raising funding for it, doing all the engineering. Big team of people worked on it. So I don't know if that answers your question. That's about Demos in particular as an instrument. It has some wonderful features, including things that have never been really done on spectrographs before. But the concept of a spectrum using, let's say, something like a prism to create a spectrum, that goes a very long way back. That, of course, the concept of creating a spectrum is much older than that. Much more than 22 years old is what I'm saying.
Yeah. So like this technology must have, helped a lot in gathering more accurate data. Like, is that
That's
right?
correct. That is
Yeah.
correct.
Yeah.
And different ways of accurate. So one of the ways in which spectroscopy has evolved is you can get very high resolution spectra now, where you split things very, very finely into different colors. If you think of the 7 colors in a rainbow, you can split up the light between violet and indigo into 10 colors. You can split it up into 1,000 colors. You can split it up into 1,000,000 colors. the more finely you split it, the higher the resolution of the spectrograph. So that's been one of the directions of evolution. Other direction is how sensitive a spectrograph is, how faint a star can or galaxy can measure a spectrum for. Those are the sort of common directions of evolution of technology.
Okay, that's good to know. It's fascinating.
Thank you. So I'm just looking at this star over here. And if you look closely, it has these two very strong dips here produced by sodium. And it turns out that when you see these dips, it means it's not a red giant star in Andromeda or a red supergiant, but rather this is a foreground star in our own Milky Way. So I'm going to make a note of that. You're probably wondering what gibberish I'm typing into this file, but it has just a few notes about decisions about the star, what information we have, instrumental issues with the spectrum sometimes, but also some astrophysics information about what I see in the spectrum and what it's telling me. I won't remember afterwards unless I write it down. That's why I'm writing it down. This star is also in the foreground. You can see this vignetting problem is really bad for it. But again, I'm saying this is in the foreground because of the presence of this, what's called the sodium doublet, this double sodium dip over here. These two, ignore the blue line also has it, but the white line is stronger. This dip is a sign that it has sodium and also has titanium oxide. You can see this sort of these very sharp drops are produced by titanium oxide. And then it also has the calcium triplet. Where is the calcium? It has two of the three calcium lines. The spectrum is truncated, so I should make a note about that.
Yeah, I noticed that there's like white lines and then blue lines in the spectrum. So
Yeah.
the colors is there any significance to it?
Yeah, so the white line is the spectrum of the star in Andromeda. The blue line is what is called a template, where we take a spectrum of a bright star in the Milky Way whose velocity we know. We have a library of such spectra. All of those spectra are Doppler shifted so that they're at zero velocity. And then we use these templates. We take each of these templates. I think we have 15 of these templates. You can see, or 16, 0 through 16. We have 16 of these templates. And we take each of these template spectra and we compare each of the 16 to the spectrum of the star in Andromeda. And we allow for different Doppler shifts. And through that, we learn what kind of star it is that we are taking a spectrum of in Andromeda. From the spectrum, we learn what kind of spectrum in the Milky Way best matches it, and then how much the Doppler shift is. That the latter is a measure of the velocity of the star.
Okay. Okay.
Hey, Raja, so we are opening right now. We've
Oh,
seen
fantastic, fantastic.
some reduction in counts for the internal sensors. However, it does also look like the humidity is starting to come back up. So we'll see, hopefully.
But I'm glad to hear that the internal dust counts are going down. That's good.
Yeah.
That's what you want to see, right?
Yes.
Yeah, how did we find out that those tips are produced by sodium and titanium? This is a very good question. The way you find out is in the laboratory, people take different elements, they shine light. They take different elements, convert them to gas form. So you have a gas cloud of sodium, titanium. You shine light through it, and you see at what wavelength that light gets absorbed. This is called laboratory spectroscopy. So you can associate dips in the spectrum at different wavelengths with different elements. Every element has sort of a fingerprint of dips in the spectrum. And when we see particular dips in the spectrum of a star, we can associate them. Good thing is, while there are many elements in the periodic table, most of them are very rare in stars. So the common elements are things like sodium, titanium, oxygen, carbon. Those we just need to know what kind of spectral dips they produce, and that too under certain conditions. Stars' surfaces are never they're within some range of temperature. So as long as we're talking about laboratory experiments, we mimic the same range of temperatures and see. That's how we know a certain dip is produced by sodium versus another one is produced by titanium. I hope that answers your question, Nehal. Elisa, do you have the VNC software running? Or would you like me to run it from my computer also?
I have it running from the other computer, not from
Okay.
this one. Yeah.
Got it. Okay.
So we are getting ready to open
Fantastic.
to run the tests. So we don't know if we are going to upset.
Right. So just for the folks on the shadow session, Julie and Cassie are opening the dome. So the telescope sits inside a dome. It's got what looks like a giant garage door that opens and closes. Let me see if I can show you a picture. These should contain pictures of the, let me see if I can find one. Yeah, the Subaru catwalk picture should show it. You can see this sort of, do you see the garage door opening near the end of the video? That's actually our telescope opening, I think, right, Julie?
You aren't sharing your screen,
Oh, I'm
Raja.
not sharing my screen. Sorry about that. Happily
Not sure
enjoying
which
this.
video. You might be seeing K1 if you're looking at the Subaru live camera.
Is
K2 is in
K1
the
closer to
background.
Subaru?
Yeah, K1 is closer to Subaru.
Yeah, I think we're seeing K1. You see, it's like a garage door opening near the end of that video.
Yeah, that's K1.
That's K1. And I guess K2's, you can also see K2 opening actually if you look closely, because you can see at the top, the top structure. I mean, the slit isn't facing us, but if you look closely, I think I could see K2 opening too at the very end. Or maybe K2 hasn't been opened yet, or has it?
No, I have K2 open. I'm not sure which Zoom I should talk to.
Oh, sorry.
K2 is open. The dust counts are coming down really nicely. So I basically have both. I'm glad I'm not getting any feedback. I hope you guys
Okay.
aren't either.
I'm good. I'm good.
The dust counts are coming down really nicely. I was actually going to say, go ahead and highlight the first star where you want to focus near, and I probably should go ahead and start moving there because it's looking like this was a successful experiment. And all
That's
of our counts
fantastic. I'm
are,
so happy to hear that.
Yeah, me too.
Yeah, so this dome is being opened. This is Keck II. This is the telescope we're using tonight. The height of this dome, by the way, is something like a 10-story building. They're huge.
Raja,
Yeah.
we have about 8 minutes left in the session. Did you want to go ahead and wrap up with maybe talking about what you all are, what the next steps are, with the observations now that things are open?
What we're doing is we're taking a series of long exposures, 20 minutes, half an hour, series of them on a single galaxy in this class of galaxies that are called ultra-diffuse galaxies. So that will start soon once the telescope is lined up, right, Elisa? The science exposures haven't started yet, or?
They just started.
Just started, okay. And we'll just sit on this galaxy for the rest of the half night. That's the plan. The idea is to take that light of the galaxy, put it into the spectrograph, KCWI, and get a measurement of how rapidly stars are rattling around inside the galaxy, because that tells us about how much dark matter it contains. We're also hoping to learn from the spectrum about the age and chemical composition of the stars that make up the galaxy. Lisa, am I missing anything? UDGs?
No, those are the goals of the project. Yes.
Again, I'm sorry, folks, that we don't get to show you KCWI data because we're just starting a long exposure now, and nothing until that finishes, there'll be nothing to see.
You do have a session coming up next month, will you be continuing these kind of the same observations, looking at UDGs?
For us, no, this is the last half night for this semester. We have time in September, October, and November, Jamaica. We got granted a full night in September, one half night in October, 2 half nights in November. I'll send you those dates soon. But,
okay. Sorry, I was looking at another group who have Keck.
Right.
That's Sophia's group, sorry.
Okay, no problem,
That's
no problem.
Okay, well, we will certainly look forward to joining you all again later in the year. And in the meantime, could you drop a link to one of your more recent papers, the one you've shown before with Elisa and one of your other colleagues who's not here today?
Sung Soon, and yeah, let me see if I can. Elisa, do you have a link to your UDG paper handy?
Let me find it.
Thank you.
Thank you.
They put it in the chat.
Thank you, Elisa.
Perfect, thank you. So we can follow along and get some more in-depth background on all the wonderful research that you all are doing so that we can maybe talk to you about it and follow up on some things later in the year.
Thank you so much.
Thank
Thank you
you
all for your
all.
patience.
Yes, we appreciate you and look forward to seeing you in a future Shadow the Scientist session. Yes, thank you, Rob, Cassie, Julie, thank you so much. Nihal, thank you, everyone.
Alankrita,
Thank you so much. We hope the rest of the evening goes smoothly.